biggest changes that we've seen as a manufacturer is shift in the way that we're moving air. So housed fans, everybody's probably pretty familiar with the forward curve belt driven housed fan style. Used to be all favorable on price. You had to build this fan though in a certain arrangement in order to get end discharge, top discharge. We're seeing a shift in the market, and as a manufacturer, all the way up to 25,000 CFM at Greenheck, we have standardized on these direct drive plenum fan offerings now. So fan scroll housing, you're pressurizing the actual scroll itself and generally belt driven. Where now with a plenum fan, you're actually pressurizing a cabinet. So almost endless discharge arrangements that you can do. And with direct drive fans, a lot less maintenance required because there's no more belts and shivs to adjust. You've got a wheel mounted directly on a motor shaft, and then variable frequency drives are typically standard with those, where it would be an option to select with a forward curve belt driven fan option. And then other things that we kind of see here as far as benefits on the plenum fan, I mentioned this already, that scroll fan needed to be built in a certain arrangement and you were limited to either end, top, and bottom. With a plenum fan, since we're pressurizing the cabinet, basically just give us an opening and now we can do left and right side discharge as well. And in some cases, say we make a mistake, the unit is ordered as end discharge, gets out into the field, and you say, you know what? It would be really nice if we could actually turn this unit sideways and come out the side. Most of those panels are typically interchangeable, so you can just swap the panels out. Opens up your discharge arrangements and your flexibility in the field. Okay, so other thing to discuss is the overloading aspect of fans and kind of the victims that we all are in the design side. I'd be surprised how many jobs come across my desk laid out at a 1/2 inch of external static pressure or a 1/4. Seems like there's general rules of thumb always kind of laid out with these systems, but it's not always the case that, especially with Make-Up Air, there's usually very little resistance on the discharge end of these, so very little external static pressure. Obviously, that's not going to be the case every time, but if you don't have any ductwork hooked up to these systems, say even if you have a factory provided 3-way or 4-way diffuser, as a manufacturer, we calculate that static pressure into the system already. So that system, if it's ordered at 10,000 CFM, should actually be ordered if it's going to be a through-wall design and the weather hood is just simply extruded on the outside of the unit and then we're just throwing air into that building. We're going to want to make sure to lay out that system at 0 inches of external static pressure because there's nothing else for the unit to overcome. But unfortunately, we see this all the time where, ductwork or safety factors are kind of built into it, or just throw a 1/4 inch on it as a just in case. The problem is we set up the unit to hit the certain fan RPM and hit the design CFM that it was actually selected at. So we're trying to account for that static pressure. And if it's not there, this is an example of a forward curve fan. The blue line is your system curve. Your operating point is the circle. So if we take a look at perfect scenario, real world situation where, all right, we've calculated our static pressure and our system now with internal static pressure and external static pressure, we're just under 2 inches total water column, and we want to move 10,000 CFM. Now we follow that line down to the dashed black line. That's where our brake horsepower is going to be. So for this particular forward curve fan at just around 2 inches of total static pressure, it's going to require right around 8 brake horsepower to move that airflow at 964 fan RPM. Real world scenario though is, all right, we calculated for a 1/2 inch of static pressure that actually doesn't exist. So now we set that unit out on our rooftop, and naturally we're going to move more airflow than what was originally laid out or designed because it was laid around 10,000 CFM. It doesn't have that resistance to overcome on the other end. So now we're moving more closer to 12,000 CFM. And then with a traditional forward curve fan, it is a overloading design. So now we trace that up and we're moving more airflow and we're right at that 10 horsepower. So at original selection, we were at 8. Probably felt pretty confident laying that system out with a 10 horsepower motor. Well, now you're right at the FLA or the overload state of that fan. So now good luck even getting an air balance done to calculate that you're just under 12,000 CFM to dial that system back with that static pressure not being present. So it risks an overload state. This is where VFDs really become crucial to be able to just dial in an air balance with just simple parameter changes rather than changing out belts and shivs. But again, it's just trying to understand that sometimes static pressure we're over designing or over calculating for some of these systems. Now, the benefit of moving to a BI or an MF mixed flow plenum style wheel is that same design now at 10,000 CFM, just under 2 inches of total static pressure. Now we follow that brake horsepower line. We were at 8 horsepower just as a standard design. The huge benefit of this fan type already is now we're moving significantly less brake horsepower at the same design with this fan type. So you're just under 6, so you can confidently lay out a 7.5 horsepower motor where you were forced to a 10 horsepower motor right out of the gate with that belt driven fan option. Now that same scenario exists in here in this case where half inch of static pressure maybe doesn't exist. Well, we're moving more airflow than design, right around that 12,000 CFM. But the fan curve and the brake horsepower curve kind of breaks the standard laws that we're used to. Believe it or not, we're moving more airflow than design with less resistance, but we're actually moving less brake horsepower. So it can easily be balanced. You're not in that overload state. You're actually operating less overall brake horsepower, but a test and balance guy can easily get in there and dial that system back to that design 10,000 CFM. So it's a non-overloading design. And this is the reality of most product selection, unfortunately. Again, many jobs come across my desk laid out at a half inch and a quarter. We're victims of always overestimating or compensating for static. And if it's not there, that system's going to move too much air. And the only solution to that is slowing these fans down. Now, the downfall to anything on a forward curve fan, which is still going to be in your 25,000 CFM and higher airflow ranges, is anything that's above 10 horsepower, you're now in fixed pulley arrangement. So there's no more drive adjustability on the motor side to be able to slow a fan down by turning a pulley in or out a half a turn at a time. They're fixed pulleys. So if you're in that overload state, first off, you're throwing a dart at the system to just try and calculate what shivs need to be changed out if you don't have a VFD. And then you're trying to balance the system down from there. So another benefit of mixed flow fans, direct drive fans, but also just considering putting VFDs on these very large systems that have fixed pulley arrangements, and considering putting the drives built in to just simply slow down that fan speed by changing the frequency output to the motor rather than having to change out belts and pulleys.